So if you thought the one-dimensional elastic collisions we looked at in the last video was bad, things are about to get even worse. Because now we're going to say, what if we have two masses, mass 1 that's moving to the right with some velocity v, and mass 2 that's slightly not aligned with it. So in other words, after the collision, we have mass 1 goes off at some with some speed v1, mass 2 goes off with some speed v2, where mass 1 makes some angle theta and mass 2 makes some angle phi. Okay, so now we have a two-dimensional problem, and again we still have two unknowns, the vector v1 and the vector v2. And so again, to solve this, we start exactly like we did for just a one-dimensional elastic collision. We say we know momentum's conserved, right? Anytime we have some kind of collision, we always want to look at conservation of momentum. So initially, we just have mass 1 moving to the right with some velocity v. So its x component is v and its y component is 0. Okay, after the collision, now mass 1 is moving with a velocity v1. The x component is v1 cosine theta. The y component is v1 sine theta. And then the momentum of particle 2 is mass 2. The x component is v2 cosine theta. And as we all remember from our vectors exam, the y component is a minus v2 sine phi. I'm sorry, this should have been a phi as well. Right? So this is what conservation of momentum gives us. And then the other equation that we have is 1/2 m1 v squared is equal to 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Okay, so notice again that the only two unknowns we really have is the speed v1 and the speed v2, because the other parts of the vector are just given by the trig functions, cosine theta and sine theta. So we do have to know these angles, or we can be given v1 and v2 and not the angles, or some combinations of these. The only thing that we'll note in this is that this v squared, remember, is really v dot v. So in this case, it actually, so for the left side, we really have a 1/2 m1 v squared. But we notice for this term, right, the v1 squared is v1 dot v1. Okay, so this is 1/2 m1 v1 dot v1, right, is v1 squared times cosine squared theta plus sine squared theta. Well, this is also 1. This is a trig identity that you may or may not know. Cosine squared theta plus sine squared theta is 1. So this is actually true for the speeds as well, and we see that by taking the dot product. So this kinetic energy equation holds. So now we have two equations and two unknowns, and so from here you just solve for v1 and v2. And you can see your book for this solution. Your book works out the general solution for a two-dimensional case where you have one particle moving and the other isn't. It's just a long calculation, and there's nothing for you to really gain by watching me do it, because your book, has it written out just as well as I can write it out for you. So that about wraps it up on collisions. There isn't a whole lot here, because most of the stuff you already saw when you took your conservation of momentum exam. The only thing that now we've added is this idea that you can have, conservation of energy in some cases and not conservation of energy in others. So I'm going to have a couple examples because I think that those are going to prove useful for you. But this is all really the new material that you have in this unit.